Date 2024, question 27. If the Prandtl number is 0.01, which is very small, even air value, Prandtl number for air is around 0.5, 0.6. Anyway, this is very small. Which of the following statements are true? We know that Prandtl number is a ratio of momentum diffusivity divided by thermal diffusivity. This, of course, we know is equal to mu over rho. When we use the viscosity, rho is the density, and this is the ratio of K over rho Cp. K is the thermal conductivity, rho is the density, and Cp is the specific heat of the substance. Anyway, so Prandtl number is the ratio of the two diffusivities, momentum and thermal, and this is 0.01. So quite automatically, the momentum diffusivity, since it's such a small quantity, momentum diffusivity is much smaller than the thermal diffusivity, and therefore D is the correct option. So this is true. Secondly, we know from Bloch-Shears and Paulhausen approximation, they have done an approximate analysis of the momentum and the thermal boundary layer together. For Prandtl number less than equal to 1, this can be approximated as Prandtl number raised to the power 1/3. Since Prandtl number is very small, so this would be 0.01 raised to the power 1/3, which is again a very small quantity. So we can say that the thickness of the momentum boundary layer is much smaller than the thickness of the thermal boundary layer. So diagrammatically, very approximately, if this is my flat plate, uh, we know that the boundary layer definition is when it just attains 99% of the free stream velocity. Let's say this is my free stream velocity V infinity. So let's say this is delta, and when there is similarly when the fluid attains 99% of the free stream temperature, let's say right here, so that's a thermal boundary layer thickness, so that's delta T. So we can say that the momentum boundary layer thickness is much smaller compared to that of the thermal boundary layer. So this is also true. So therefore, B and D are correct options. This is false and C is also false.